This is Biomaterials, Lecture 10, Video 2. Let's go over the solution to this problem. If we take a look at Fourier's law, we already know K for each of the materials being considered here. We now need to determine what is the derivative of T with respect to X in this case. We are assuming steady state heat transfer with no internal energy generation and uniform properties in the material. Therefore, if we take a look at the temperature versus position graph shown here, we just need to determine its slope. The slope can be calculated by determining the change in temperature and dividing it by the thickness of the crown, which is 0.005 meters. The change in temperature is T sub 2 minus T sub 1. So it is 37 degrees Celsius minus 85 degrees Celsius, which is equal to negative 48 degrees Kelvin. This is why there is a negative sign in Fourier's law. Gold, which has a relatively high thermal conductivity, will have a high heat flux, greater than 2.8 million watts per meter squared. Enamel will have a much smaller heat flux of 7,802 watts per meter squared because it has a much lower thermal conductivity. Therefore, heat transfer by conduction will be much higher for the gold biomaterial than it is for the natural enamel, which is a biological material. So, why is there a difference in thermal conductivity between gold, a metal, and enamel, which is mainly hydroxyapatite or a ceramic? To understand differences in thermal conductivity, we have to discuss the mechanisms of heat transport in solid materials. Heat is transported in solid materials by two mechanisms: the motion of free electrons and vibration waves in the crystal lattice. The thermal conductivity K in Fourier's law actually takes both of these mechanisms into account. K is actually the sum of the thermal conductivity due to electrons, which is shown here as K sub E, and the thermal conductivity due to lattice vibration waves, which is shown here as K sub L. Let's focus on electrons. Free electrons from the hot portion of a solid absorb energy in the form of heat and transfer that energy through collisions with electrons in the colder region of the solid. In Engineering 86, you learned that metals have free electrons due to the nature of metallic bonding. Because metals have a relatively large number of free electrons, they have a relatively high electrical conductivity. Well, materials that have a large number of free electrons also have a relatively high thermal conductivity. The graph here shows an almost linear relationship between the electrical conductivity and thermal conductivity of materials. Note that materials with a higher electrical conductivity have a high thermal conductivity and vice versa. The table shown on the right contains data on the thermal properties of certain materials. Note that most of these materials have thermal conductivities in the hundreds of watts per meter Kelvin. The bottom line is that heat is readily conducted through metals because of the high numbers of free electrons in their structure. If you are interested in reviewing the electrical properties of materials, links to the relevant lectures are provided in the description below. Let's now focus on the other mechanism of heat transport in solids, which are phonons. Phonons are collective vibrations of atoms within solids caused by thermal excitation. In the previous lecture, we discussed how the vibrations of atoms about their equilibrium position is behind thermal expansion. Well, the collective vibrations of atoms in a crystal is another way that heat is transported through that crystal. The magnitude of the vibrations of atoms depends on bond strength. If we think of strong atomic bonds behaving like really stiff springs, Well, these really stiff nonlinear springs are efficient at transmitting vibrations due to the increased temperatures from a hot side of a material to a cold side of a material. When one atom in a strongly bonded solid is vibrating, that motion is coupled to that of a neighboring atom, which then transfers that motion to a subsequent neighboring atom, and so on. For solids with relatively weak bonding between atoms, the bonds behave like compliant springs that are not as capable of transmitting motion relative to strong bonds. If an atom on the hot side of a solid vibrates, the motion does not get transmitted as well to a neighboring atom if the bonds are weak. Any motion the neighboring atom experiences then does not get transmitted as well to a subsequent atom, and so on. In the graph that you see here, the peak thermal conductivity of silicon is less than the peak thermal conductivity of diamond. Silicon and carbon are both mainly covalently bonded solids that have minuscule numbers of free electrons relative to metals. So heat is transferred in these materials mainly through phonons. However, the strength of a carbon-carbon bond is about 1.5 times stronger than the strength of a silicon-silicon bond, which means that heat transport by phonons through diamond is much better than silicon, which results in a higher thermal conductivity for diamond. Now that we've discussed the two mechanisms of heat transfer, we can now discuss how the structure and composition of materials can impact the material property that is thermal conductivity. Let's first focus on phonons. Anything that interrupts the perfect periodicity of a crystal lattice can scatter a phonon and reduce thermal conductivity. So, what can scatter lattice vibrations in a solid material? Grain boundaries can certainly scatter phonons and reduce thermal conductivity. In a perfect single crystal with strong bonding, lattice vibrations caused by elevated temperatures on one side of that crystal can be transmitted unimpeded through the material and to atoms on the cold side. However, as you learned in Engineering 86, a vast majority of materials used in engineering applications are actually polycrystalline, and grain boundaries in polycrystalline materials can disrupt the lattice vibrations in the materials. Therefore, polycrystalline materials have lower thermal conductivities than single crystal materials. A link to a relevant Engineering 86 lecture on polycrystalline materials is provided below if you'd like to review polycrystalline materials. In Engineering 86, you also learned about zero-dimensional point defects like substitutional and interstitial impurities. Well, these impurities can also scatter lattice vibrations in a material. The data that you see here is a graph of thermal conductivity as a function of nickel content in a copper-nickel alloy. Here you see the highest thermal conductivities are exhibited by pure copper and pure nickel. Thermal conductivities begin to drop as nickel is added to copper and vice versa. Thus, pure materials have higher thermal conductivities than alloys. In case you are wondering why the thermal conductivities of copper and nickel shown here appear lower than the values on a previous slide in this lecture, note that the units of thermal conductivity shown here are in watts per centimeter Kelvin. 2- and 3-dimensional defects can also scatter phonons and reduce the thermal conductivity of materials. The image that you see here was taken from a paper that is linked in the description below. Reading the paper is not required, but in a nutshell, researchers were able to adjust the thermal conductivity of silicon by etching tiny holes in the material. These holes disrupted the transmission of heat by phonons in that material. Lastly, phonons themselves can scatter other phonons. The more a material vibrates, the harder it is to transmit a lattice vibration through that material. As more phonons are produced in a material and their amplitude increases, the scattering of phonons by other phonons also increase. If we take a look at this data, you can see that the peak thermal conductivities of aluminum and copper are achieved at about 10 Kelvin. Heat is transported by both electrons and phonons in metals. And as temperature is increased, thermal conductivity in these materials drops because phonons are scattering other phonons. The same can be said about silicon, germanium, and diamond, which are materials with mainly covalent bonds. So heat is transferred mainly by phonons. On the graph on the right, you can see that the peak thermal conductivities for these materials occur below 100 degrees Kelvin. The thermal conductivities for these materials at room temperature are much smaller than they are at very low temperatures because the phonons in the materials are scattering other phonons. Let's take what we've learned and apply it to daily life. If you enjoy coffee, tea, or hot chocolate, you have probably taken sips of these hot beverages using a ceramic mug. Take a look at the thermal image on the left. The temperature scale is shown, and you can see that there is a hot beverage inside the mug. But the outside surface of the mug remains relatively cool enough to touch. Thermal conduction is certainly happening from the inside surface to the outside surface because of a temperature gradient. But the thermal conductivity of this ceramic mug is so low that the heat flux, as calculated by Fourier's law, is also relatively low. The low thermal conductivity of the mug prevents the heat of the liquid from rapidly penetrating and dispersing into the mug. So touching the mug won't be painful, which is why the person in the picture on the right can relax while sipping a hot drink. Furthermore, another reason for using ceramics for hot drinks is because we typically want our hot drinks to stay warm. Having a material with a low thermal conductivity means that less energy is lost to the environment. You should now have some understanding of why we use ceramic mugs for hot drinks. Properties of material are always linked to its structure at the atomic level. Ceramics are electrical and thermal insulators because they lack large numbers of free electrons. In ceramics, phonons are primarily responsible for thermal conduction. Thermal conductivity has a phonon contribution and an electron contribution. And in ceramics, this phonon contribution dominates. However, relative to electrons, phonons are not as effective as free electrons when it comes to transferring heat energy. Furthermore, we just discussed how phonons are scattered by lattice imperfections and defects. The more amorphous a material, the higher the scattering, the lower the thermal conductivity. If you've ever broken a ceramic mug and had to clean it up, I hope you had the chance to take a look at what that mug looks like below the surface. Visually, you can see a rough surface, and if you were brave enough to touch it, you could feel its roughness. At the microscopic level, a ceramic mug has pores and a highly amorphous structure. Phonons have a challenging time moving through such a microstructure. This is another fine example of the relationships between the structure and properties of materials. Now, ceramics are not your only choice when it comes to containers for hot beverages. This is a tin cup that was used during the Civil War, and you can still pick these up online. However, please be careful when using tin mugs when drinking really hot beverages. Here's why. The thermal conductivity of tin is 10 times higher than the thermal conductivity of the ceramics used in mugs. Your hot drink will not only get colder much faster in a tin mug, but it won't be as enjoyable holding the drink in your hand. Why is the thermal conductivity in metals so much higher than in ceramics? Well, we already discussed the answer, but let's talk about it again. Metals like tin have a relatively large number of free electrons due to the nature of metallic bonding. Heat transfer by electrons is much more efficient than heat transfer by lattice vibrations. Electrons are not as easily scattered as phonons, and electrons move through a solid much faster than phonons. Furthermore, there are much more free electrons than phonons in metals that can participate in thermal conduction. However, note that you can process materials and change their properties. Adding impurities to pure metals can change their mechanical, thermal, and electrical properties. For example, adding nickel to copper can improve mechanical properties, but can also result in reduced thermal conductivities and reduced electrical conductivities, which is shown here as increased resistivity. The impurities not only scatter phonons, but can also scatter electrons, which is why both electrical and thermal conductivity drop as the amount of nickel in copper is increased. What about polymers? Polymer mugs certainly exist. Additionally, some polymers have much lower thermal conductivities relative to ceramics. So, why is this the case? In Engineering 86, we covered the structures of polymers. Some polymers can have a highly amorphous structure, while others can be partly crystalline. Other polymers can be slightly cross-linked, while others have a high degree of cross-linking. These structures result in a significantly lower thermal conductivity in polymers. When I say low thermal conductivities, I mean really low. Take a look at the thermal conductivities for some widely used polymers on this slide. All of these values are below 0.5. Compare these values to the thermal conductivity of 3.8 for the ceramic mug and 38 for the tin mug. These are really low. Recall that heat transfer in solids is due to electrons and phonons. Because polymers don't have crystalline structures like metals and ceramics, heat transfer in polymers is actually accomplished by the vibration and rotation of polymer chains. Therefore, the magnitude of thermal conductivity in a polymer depends on the degree of crystallinity in the polymer. Highly crystalline and ordered polymers have greater conductivities than amorphous polymers due to the more effective coordinated vibration of chains. As you can see on the graph shown here, as a polymer becomes more amorphous, its thermal conductivity drops significantly. Thermal conductivity in amorphous polymers can be reduced even further through processing. Introducing small pores and creating a cellular structure further lowers thermal conductivity. As you can see here, foamed polystyrene has 1/4 the thermal conductivity of non-foam polystyrene. So great! Why don't we see more polymer mugs so that we can keep our drinks hotter for longer periods of time, all while keeping our hands cool? Well, in Engineering 86, we discussed the melting and glass transition of polymers, which are relatively lower than those exhibited by amorphous glasses. Above the glass transition temperature, it is relatively easy to deform polymers and cause them to lose their shape. The image on the right is one that I took after I wasn't thinking in the Harvey Mud Cafe and decided to pour excess coffee into a plastic cup because I was rushing to class. I barely touched this plastic cup with the coffee in it, and look how easily it deformed at elevated temperatures. Polymers have very low thermal conductivities, but they are not ideal for holding hot drinks. Now that you're familiar with the thermal properties of various materials, let's talk about composite structures, where different classes of materials are in intimate contact. These structures are certainly present in medical devices and biomaterials applications. Metal fillings and teeth are in intimate contact with enamel, which is mainly composed of the ceramic hydroxyapatite. Artificial hips can consist of titanium components bonded to ceramic components. In artificial knees, polymers and metals are constantly in contact with each other. Now, thermal properties are less critical than other material properties in these applications, but there are many other engineering applications where multiple classes of materials are used because of their thermal properties. For example, processors in computers generate a lot of heat. One way to dissipate the heat is to place the processors in contact with metal fins, which can get rid of heat efficiently through conduction and subsequently convection and radiation. Sometimes we want to keep fluids warm, such as in pipes used to transport hot water to a shower or sink. In such situations, we want to wrap copper pipes, which have a high thermal conductivity, with a polymer foam, which has a very low thermal conductivity. This reduces heat losses to the surrounding environment. We can determine the heat flux through such composite structures. Before we begin this discussion, let's go back to Fourier's law, which is seen here. Let's look at another form of Fourier's law, which we can use to calculate the heat transfer rate through a material. As you can see, this is merely the heat flux multiplied by the cross-sectional area, A. Heat transfer rate has units of energy in joules per second or watts. If we further assume that the plane wall has constant properties throughout and there are no sources of internal energy generation or heat sinks, then the derivative of T with respect to X simplifies to the temperature difference T sub S2 minus T sub S1 divided by the thickness of the plane wall, which is L. This is a very useful form of Fourier's law when it comes to composite structures. Here's why. Remember back in Engineering 79 when you learned about Ohm's law and KCl? If you don't, the slide is shown here. Recall how we calculate the resistance of a resistor in the circuit that you see here. We take the voltage drop across a resistor and divide by current, which is Ohm's law. If you get a negative resistance, then you change the direction of the current in your loop to get a positive value. Let's go back to Fourier's law. We can rewrite the equation so that we have the temperature drop from one side of the wall to another side of the wall divided by the heat transfer rate Q sub X. This equals the thickness of the plane wall divided by thermal conductivity times area. Some of you may already be seeing this, but there's an analogy between the transfer of heat and transfer of electrical charge. Here you see a temperature drop, which is like a voltage drop. Here you see a heat transfer rate, which is analogous to current. Just as an electrical resistance is associated with the conduction of electricity, a thermal resistance, or R sub T, may be associated with the conduction of heat. Here are the equations for electrical resistance and thermal resistance shown side by side. We can therefore define a resistance as the ratio of a driving potential to the corresponding transfer rate. So again, just like electrical resistance equals a voltage drop divided by current across the resistor, thermal resistance equals a temperature drop divided by the conduction heat transfer rate across that material. In 1D steady-state conduction, heat transfer through a material with constant properties and no internal heat generation, we can treat the material like a resistor. The thermal resistance is equal to the thickness of the plane wall divided by thermal conductivity times the area of the plane wall. Let's go back to Engineering 79 once again. If you have resistors in series, you can collapse these resistors in series to a single resistor. The equivalent resistance of the single resistor is equal to the sum of the resistances of the three resistors. Resistors in parallel can also be collapsed into a single resistor, which has an equivalent resistance, R sub EQ, that can be calculated using the equation shown here. In one-dimensional, steady-state conduction, heat transfer through a material with constant properties and no internal heat generation, we can treat the material like a resistor. Therefore, rules for resistors in series and parallel also apply to thermal resistances. Here you can see three different materials in a composite structure can actually behave like three resistors in series. In the figure on the right, you can see how various sections of this wall behave like resistors in series and resistors in parallel. Again, the key assumptions here are one-dimensional steady-state conduction through materials with constant properties and no internal heat generation. With these assumptions, we can model materials like resistors. Let's apply what we've learned. So, rules for resistors in series and parallel also apply to thermal resistances. A composite wall consists of three different materials which have different thermal conductivities and lengths. We can simplify the composite wall as a single wall with the same boundary conditions of T sub S1 on the left and T sub S2, which has an equivalent thermal resistance R sub T total. What is this equivalent thermal resistance? Your options are shown here. Please click on the link below to complete this in-lecture question and receive credit for your work. This is an open book, open note assignment. You may take as much time as you need, but the important things to remember in these in-lecture assignments are that you do not ever hit the back button on the form and you complete the questions before starting Lecture 10 Video 3. We trust you to follow the honor code. We will go over the solutions to this problem in Lecture 10 Video 3, which is also linked below.